Hello friends, we are going to discuss here unit number 4, that is algebraic system. So some important points we are going to discuss here. So basically what is meant by algebraic system? So you can see here, so the algebra or algebraic system which is having n array operations for n is equals to 1 to 3 on the set x. Mapping of the operations from x raised to n to x, n is equals to 1, then it is called as a unary operation, and whenever n is equals to 2, then it is called as a binary operations. So for example, let us consider the algebraic system which is represented by this notation s comma f1 f2 up to fn, where s is nothing but the non-empty set and f1 f2 these are the operations on the set s. Okay, so that operations may be that meet operation, this delta is there, unary plus is there, join operation is there, and most importantly is what, x is the non-empty set where x1 and x2 these are two elements belongs to x, then we can perform x1 star x2. So that is nothing but the representation of the algebra or algebraic system. Fine. Now talking about the algebraic system, you can see, let I be the set of integers. Consider algebraic system ordered pair I comma plus comma multiplication. So what actually we have given here, one set is given to you, that is I, non-empty set, you can say the integers. So as I mentioned here, integer may be of even integer, may be the positive integers and all negative integers. Any type of integers may be given to you, and you have to check for which condition it is algebraic system and which is not algebraic system. So basically whenever two operations are given to you, that is plus and multiplication, assume here that set I which containing three elements a, b, c, it must be follows these properties. The first one is the associative property. In the case of addition, if a, b, c belongs to capital I, then it should gives here in bracket a plus b bracket complete plus c, which must be equals to a plus in bracket b plus c. That is the first one, that is associative property. Next one, commutative property. If a and b belongs to capital I, then a plus b must be equals to b plus a. Talking about identity element, as we are taking here addition, we are taking here 0 as an identity element. So 0 and a belongs to capital I, then it gives here a plus 0 is equals to 0 plus a, which gives you a. Okay. Next property is inverse element. For example, if a is the given element and minus a is the inverse of that element, which both are belongs to capital I, then a plus minus a, which is equals to 0. That is in the case of addition. Now similarly, as the second operation we have taken, the first operation was addition, second operation we are taking here multiplication. So in the case of multiplication, some properties are, you can see here, if ABC belongs to I, then in bracket a cross b cross c, which is equals to a cross in bracket b cross c. That is the associative property. If a cross b belongs to capital I, then a cross b, which is equals to b cross a, that is the commutative property. So as we are taking here multiplication, we are taking here 1 as an identity elements, means a cross 1, which is equals to 1 cross a, which is a. That is the identity element. So here 1 is the identity element. And the next one important property, that is the distributive property. So what the distributive property says? So distributive property is what? If a, b, c belongs to capital I, then a cross in bracket b plus c, which gives you a cross c, a cross b plus a cross c. Okay, so that is the distributive property. So keep in mind that whenever the question will be there, means define algebraic system and closure properties of the algebraic system. So you have to write down what is meant by algebraic system. Simply algebraic system, which is denoted as ordered pair s comma f1 comma f2, where s is the non-empty set and f1 f2 these are the some algebraic operations. So we are considering here one example, that is ordered pair I comma unary plus comma multiplication, And under the discussion of unary plus and multiplication, we are considering here closure properties. In the case of addition, we are considering associative property, commutative property, identity element, and associative, commutative, identity, and inverse element. And in the case of multiplication, associative, commutative, identity, and distributive property. So in the case of closure property, you have to write down all these things. And one more thing is cancellation property. Whenever A cross B is equals to A cross C, simply A get cancelled. It will gives you B is equals to C. So keep in mind that you have to write down what is meant by algebraic system in this scenario. Then again going to this example, what actually we have to check here. See, the question is very interesting. Read this question carefully. Read this question carefully, whatever I highlighted. Let I be the set of integers. Consider algebraic system ordered pair I comma unary plus comma multiplication, where plus is the addition and cross is the multiplication. And let us take here I is equals to ABC. Now what you have to check, whether this is an algebraic system for all even integers. That is the first condition. Means we have to assume here I is equals to even integers. So basically integers, even integers means you will be take here 0, 1, 2, 3, 4 and so on up to infinity, whatever as per your requirement. So whenever you will be take the values of ABC, let's take here ABC is equals to let us say 1, 2, 3. So by taking that values of 1, 2, 3, you have to substitute that 1, 2, 3 in this equation. Then what will be happen? So let us say A is equals to 1, B is equals to 2 and C is equals to 3. So what will be happen in the LHS? First of all 1 plus 2 that is 3, 3 plus 3 that is the 6, and on the right side 1 plus in bracket 2 plus 3 that is 1 plus 5, again it is a 6. So it follows the associative property. Fine, we are talking about even integers. Then talking about commutative property. So let us take here A is equals to 1 and B is equals to 2. What will be happen? 1 plus 2 that is a LHS which gives you 3, and 2 plus 1 again it is gives you 3. Means it follows the commutative property, no issue. Then identity element. So as we are taking here A is equals to 1, if you take here 1 plus 0 which should be equals to 0 plus 1 and it will be equals to 1, means it also follows the identity property. Then inverse element. So as we are taking here A as what? 1 minus A will be minus 1. So if you take here 1 plus minus 1, it will gives you 0. Okay, so that is the inverse property. Means in the case of addition, whenever we are taking here A is equals to 1, B is equals to 2 and C is equals to 3, it is going to satisfy the condition. Now take the same scenario for multiplication purpose and check whether it is going to follow or not. So if I take A is equals to 1, B is equals to 2 and C is equals to 3, then what will be happen? On the LHS it will gives you 1 into 2 that is 2 and 2 into 3 which is equals to 6. Okay, and on the RHS 1 into in bracket 2 into 3 which gives you 6. Means it will follow associative property with respect to the multiplication. Fine. Then in the case of commutative property, 1 into 2 that is the LHS will gives you 2 and 2 into 1 again it is the RHS which having the same result. So it follows the commutative property. Now as we are discussing 1 as an identity element, so let us take here A is equals to 1. As we are taking A is equals to 1 as an identity element, rather than taking A as equals to 1, let us take here B is equals to 2. Then what will happen? B into 1 which is equals to 1 into B which will gives you 2. Means what? It will gives which will gives the A is equals to 1 as a which will gives you 1 as a identity element. Then next one, distributive property. So in the case of distributive property, what you have to do, take A is equals to 1, B is equals to 2, C is equals to 3. So what will be the LHS? So if you go for the distributive property, B plus C, that is 2 plus 3 which is equals to 6, 6 into 1 which will gives you 6. On the RHS, 1 into B, that is 1 into 2 which is equals to 2 plus, then what is sorry, on the LHS some mistake is there. Here should be 5, that is b plus c, that is 2 plus 3, 5 into 1 which is equals to 5. And on the RHS a into b is equals to 1 into 2, that is 2, and 1 into 3 which is equals to 3. So both having same, so it follows the distributive property. And talking about cancellation property, if you going for ABC and a is not equals to 0, so a into b, so 1 into 2, let us take 1 into 2 is equals to 1 into 2 again, then you can say that 1 get cancelled and it will give you b is equals to c. So that is the cancellation property. So what is our observation? You have to keep in mind that this example means what? I be the set of integers for the algebraic system ordered pair I comma plus comma multiplication, where where plus is the addition, cross is the multiplication, and you have given 3 elements ABC. So it is going to follows closure property. It is going to follows the closure property for even integers. Yes, it is follow for even integer. Now you have to check for all positive integers. So what is meant by all positive integers? Sorry. Previously we have checked this for all positive integers. Fine. Now you have to check this for even integers. So what you have to do? You have to take the even integers. Means you have to take here. Simply, you have to take here a is equals to, you can take here minus 2, that is first even integer. Then b is equals to let us take here 2, and c is equals to, let us take c is equals to 6. So all these are even integer. We are talking about this one. Okay. We are talking about the first scenario, this one. Okay, that is even integer. So by taking a is equals to minus 2, b is equals to 2, and c is equals to 6, you have to check all these properties whether it is following or not. And let us say whether whenever I is equals to all positive integers, it follows closure property or not. Fine. So if you take here a is equals to minus 2, b is equals to 2, and c is equals to 6, then what will be happen? This will be gives you 0 plus this 6 will give you 6, and on the RHS b plus c, that is 8 minus 2, 6. So it is going to follow the associative property. Then in the case of commutative property, a plus b, that is minus 2 plus 2, that is 0, that is LHS will be 0, RHS will be 0. Yes, it is also follows the commutative property. Identity element, let us take here b is equals to 2, consider b is equals to 2, and check b plus 0 is equals to 0 plus b, which is equals to b or not. Yes, it is again follows. So it is follows that property also. Okay, so it follows identity element property also. Now next one is the inverse element. So as I am taking here a is equals to what we have taken, a is equals to 2 we have taken. So what will be the minus a will be minus 2. So a plus minus a, which will be gives you 0. That is again satisfying the condition. Means in the case of addition, it is going to satisfy this condition. Now multiplication. So again in the case of multiplication, take the same values, that is a is equals to 2, b is equals to, yes, take these values, a is equals to minus 2, b is equals to 2, and c is equals to 6, and check what will be happen. So if you go for a is equals to minus 2 into 2, that will be, so I am typing here, so it will be minus 2 into 2, that is the first one. First of all you have to solve this one. Okay, minus 2 into 2, so which will gives you minus 4. Fine. Then you have to go for minus 4 into this c. C is nothing but 8, so result will be minus 32. So on the LHS it will gives you, this one is nothing but 32. 32 means minus 32. Okay. Now on the RHS, if you going for the b into c, means you have to solve this bracket first of all. Then what will be the result? Okay. So result will be 2 into 8. 2 into 8 is 16, and 16 into minus 2, which is nothing but again minus 32. So that is follows the associative law. Yes. Talking about commutative law, let us check A cross B is equals to B cross A or not. So if you're going for this one, definitely if I go for minus 2 into 2, which should be equals to 2 into minus 2, it follows the commutative law. Then go for the identity element. Let us take here A is equals to minus 2. So minus 2 into 1, which is equals to 1 into minus 2, which is equals to minus 2. So it follows the identity element. Now go for the distributive property. So as we have taken A is equals to minus 2, B is equals to 2 and C is equals to 8. So first of all, solve this LHS. So in the LHS, you have to solve that bracket, that is a B plus C. So B plus C is nothing but 10. 10 into outside the bracket minus 2 means it will gives you minus 20. Okay, LHS will gives you minus 20. Now solve on the LHS. A cross B, so that is minus 2 into 2, that is minus 4. Okay, plus minus 2 into 8, that is a minus 16. So it will gives you LHS is equals to RHS, means it follows the distributive law. And in the case of cancellation, let us take here minus 2 into 2 and minus 2 into 2, it will gives you B is equals to C. Actually that is the cancellation property. So what is our observation? It is going to satisfying for whenever I is a even integers. Whenever I is a even integers, it follows the closure property. Whenever I is nothing but all positive integers, it is follows the closure property. Now go for the all negative integers. So what is our scenario? Whenever you will be go for all negative integers, so let us take here what we are going to take here. A is equals to, let us take minus 1, B is equals to, let us take minus 3, and C is equals to minus 5. So we have taken 3 negative integers and you have to check whether it follows the closure property for negative integers or not. So very first property, associative. So A plus B plus C, definitely it will be follows. I'm going a little bit faster. Yes, it will be satisfying. It will be satisfying. Commutative, yes, definitely it will be satisfying for negative. Fine. Then identity element, yes, it will be follows. Then inverse element, yes, it will be follows. Now going for the multiplication, yes, in the case of multiplication, it will be follows over here. That is associative law will be follows, commutative law will be follows. Fine. Okay. Identity will be also follows, and it will be follows distributive as well as cancellation property. So hence you can say that it is very important question. It follows, all these follows the closure property, means whenever I is equals to even integer, it follows the closure property. Whenever I is all positive integers, it is it follows the closure property, and whenever I is all negative integer, it follows the closure property. Very important question as per the point of view to the examination. Keep in mind this one. Okay. Now going to the next point. Okay. So formal definitions we are going to discuss here. So basically we are going to discuss here what is meant by semi-group, what is meant by monoid, and what is meant by group. So basically what is meant by semi-group? So semi-group is nothing but let us say ordered pair S comma composition is called as a semi-group whenever S is a non-empty set and composition is the binary operation. S is the non-empty set and composition is the binary operation. You can see here S comma composition is called as a semi-group whenever S is a non-empty set and composition is a binary operation. Okay, and most important is what? Composition should be associative and x comma y comma z belongs to S, then it gives you in bracket x comma y composition z is equals to x comma in bracket y comma z. So that is nothing but the semi-group. So that is the formal definition of semi-group. Simply, what is the semi-group? Semi-group is nothing but the it is nothing but the algebraic system which gives you S comma composition where S is the non-empty set and composition is the binary operation, which follows the associative law where A comma B comma C belongs to capital S, and which will gives you x comma composition bracket complete composition z which is equals to x comma in bracket y comma composition. So that is the formal definition of the semi-group. Keep in mind semi-group follows associative law. Yes. Now going to the next definition, what is meant by monoid? So additional to the semi-group, Semigroup which follows the associative law. In the case of monad, monad must containing the identity element. Again it is a semigroup. Again it is a semigroup, but it having the identity element. Whenever the given semigroup having the identity element, that semigroup is said to be the monad. So that is the formal definition of monad, and generally it is represented by ordered pair M comma composition. Ordered pair M comma composition is the representation for monad, and monad having the identity element. Monad always having the identity element. You can say that every monad is a semigroup, but not necessary that every semigroup is a monad. Semigroup having only associative property, monad having associative property, along with that it having the identity element. So that is the representation of the monad. You can see here algebraic system M comma composition is called as a monad when x comma y comma z is belongs to M, x composition y composition z is equals to x composition in bracket y composition z, and E is belongs to M. So you can say this as a monad, okay, which is also represented as M comma composition comma E. No issue. Yes. So one question is there, which one is monad? Yes, definitely first one is monad, second one is monad. This one is the notation for semigroup. Fine. Now the next one, if M comma star is a monad, then there is no guarantee that the two rows and two columns are identical. Then A of I into E, which is equals to A of I, not equals to A of G into E, which is equals to A of J. Keep in mind this, that is not necessary that number of rows and number of columns should be identical. It may be vary. Now, one example, see, B of x be any set from x to x with composition operation composition, then B of x comma composition is a monad. Means, for example, if there is a one set is there, B of x is a set, and which is made up of x, and mapping from x to x is said to be monad whenever it gives you ordered pair B of x comma composition. Now next one is what? If S be the non-empty set, then P of S as a power set, then algebra P of S comma intersection and P of S comma union are also monad with S and phi respectively. So that is very important question. What is the concept over here? For example, S is the, I am repeating here, for example, S is the non-empty set, then P of S will be the power set of that S. Then whatever the power set we have got, that is the P of S with the intersection, and whatever the power set we have got with the union are nothing but monad with respect to S, that is the original set, and with respect to empty set. So that is nothing but the these are nothing but the monads. Fine. Now going to these are some additional things we will be not going to discussing here. Null property, you can see here. What is the null property of monad? If V star comma 0 or V star comma composition is a null, then V star comma composition comma intersection is called as a monad. Okay. Cancellation. If two strings alpha and beta such that alpha beta belongs to V star, then x comma alpha 1 is equals to alpha and x comma beta 1 is equals to beta. Then alpha is equals to beta, then alpha 1 x beta 1 x, then it gives you alpha 1 beta 1. Keep in mind the formal definition of the monad. So what is meant by monad? So basically monad is nothing but the algebraic system which is denoted by ordered pair M comma composition, where M is the non-empty set and composition is the binary operation. Fine. And it follows the associative property along with the identity element. Means whatever wherever that M will be present, there must be identity element. Now going to the next definition. So what is meant by group? So basically what is meant by semigroup? Semigroup, that is S comma composition or S comma star, is an algebraic system, and which may be or may not be having the identity element, but it having the associative property. Whenever semigroup having the identity element, it is called as a monad. So additional to this, what is meant by group? So group having these three properties. So you can see here a group G comma star is an algebraic system. A group G comma star is an algebraic system in which the binary operation star on G satisfies the three condition. It satisfying the three condition. First one, it must be associative, means what? Whenever x comma y comma z which is belongs to G, then it should follows the associative property. That means x comma in bracket x star in bracket y star z which should be equals to in bracket x star y star z, means it should be follows the associative property. Then next one, it should having the identity element. So E will be considered as an identity element with respect to this star operation, and it must having the inverse element, means this x and x inverse should be belongs to G. So these are the three properties with respect to the group. So in the case of group is an algebraic system, okay, which having associative property, having the identity element, and having the inverse property. Okay, so whenever it going to follows this above three properties, it is nothing but called as a group. Now the next one, group should satisfy the above properties. Now discussing about what is meant by inversible. So inversible property is what? If a comma b comma c belongs to G and a star b is equals to b star c, then you can say a is equals to c, because this b and b is repeated, that will be cancelled and you will be got here a is equals to c, where b should not be equals to 0. Otherwise what will be happen? It will become 0. Or b star a is equals to c star b, then it will gives you a is equals to c. So that is nothing but the inversible property. Then what is meant by idempotent property? Simply a is belongs to G, then a star a is equals to a. Okay, so that is the first thing. Then E is equals to a inverse into a, or which is equals to a inverse into a, or simply e into a, which gives you a. So this E will be nothing but the identity element. Keep in mind, E will be nothing but the identity element. Yes, so that is the formal definition of semi-group, monoid and group. So keep in mind, you have to write down what is meant by semi-group, what is meant by monoid, and what is meant by group. Now the next definition we are going to discussing here, what is meant by homomorphism. So already we have discussed what is meant by algebraic system. So by considering algebraic system, some algebraic system togetherly, we are going to discussing here homomorphism. And under the belt of homomorphism, lots of definitions are there, and homomorphism having different types, that is epimorphism, monomorphism, isomorphism, endomorphism, isomorphic, automorphism, congruence relation, etc. Okay, so all these things are come under the homomorphism. So whenever there will be question asked, write a note on types of homomorphism. So you should be able to write what is meant by homomorphism and going for the different types. So the first one, homomorphism, let us see here. Let us x comma composition, let us x comma composition and y comma star, these are the two algebraic system of same type. These are the two type, these are the algebraic system of same type, where composition and star are the binary operations, and one function g which is mapping from x to y, then it is called as a homomorphism, or it is called as a morphism from x comma composition to y comma star. If for any x1 comma x2 belongs to x, it will gives you g of x1 composition x2, which is equals to g of x1 star g of x2. So that is nothing but the definition of homomorphism. So what is meant by homomorphism? Let us consider x comma composition and y comma star. These are the two algebraic system of same type, and which is going to mapping with function g such a way that g mapping from x tends to y, and x1 and x2, these are the two elements belongs to capital X. Then g of x1 composition x2, which is equals to g of x1 star g of x2, then whole definition is called as a homomorphism. Why it is called as a morphism? Morphism, homo means what? Same type. As we are discussing here, same type of operations or same type of algebraic system, that is x comma composition and y comma star. And morphism means we are going to mapping from one function, that g x tends to y. So that's why it is called as a homomorphism. Then talking about with respect to the function, we are going to classify the homomorphism with different types. The first one is epimorphism. So in the case of epimorphism, all these things are same, that is x comma composition, y comma star. G is a function which is mapping from x to x tends to y, and it should having the onto property, or it having the onto property, then it is called as a epimorphism. In the case of monomorphism which having one-to-one mapping. Okay, I am going little bit faster. In the case of monomorphism, it is called as a one-to-one mapping. In the case of isomorphism, it is one-to-one onto mapping. Then in the case of isomorphic, so what is meant by isomorphic? So if x comma composition and y comma star be the two algebraic system having isomorphic mapping, that is G such a way that x tends to y, then x comma composition and y comma star is called as a isomorphic. Isomorphic means what? X and y should having equal number of elements in x and y, and they are mapping with each other, or they are one to one corresponding between each other. Then x comma composition and y comma star is called as a isomorphic. Then next one, endomorphism. In the case of endomorphism, x comma composition and y comma star, these are the two algebraic system, and if x is a subset of x, then homomorphism from x comma composition to y comma star is called as a endomorphism. So endomorphism is the terminology which is related to the subset. Then what is meant by atomorphism? In the case of atomorphism, both algebraic system, that x comma composition and y comma star, in which we should be mapped from x tends to y and there should be x is equals to y, then it is called as a atomorphism. Then congruence relation, which is related to the equivalence relation, means whenever x comma composition is the algebraic system and it having equivalence relation. So equivalence relations means what? It should follows reflexive property, symmetric property and transitive property. Then it is called as equivalence relation, and in these circumstances it is called as a congruence relation. Fine. So all these are definition which is related to the homomorphism, types of homomorphism. So keep in mind, whenever the question will be asked what is meant by homomorphism, you have to write down the definition and go with the what is meant by endo, iso, ato and so on, congruence relation and all these things. Now the next point is subgroup and homomorphism. So basically we have seen what is meant by group. So group is nothing but the algebraic system which is denoted by G comma star, where G is the non-empty set and star is the algebraic operation, and which having associative property, having identity element and inverse element, then it is called as a group. Now what is meant by subgroup? Simple. Let us consider G comma star be the any group such a way that S is the another non-empty set which is subset of G, or S is belongs to G, satisfies E belongs to S, okay, A belongs to S and minus A belongs to S. Then S comma star is called as subgroup of G comma star. So basically that S comma star which is derived from G comma star, but most importantly is what? S should containing associative property, S should containing identity element and S should containing the inverse element. So that is nothing but the subgroup. Now talking about group homomorphism, simple definition. So consider G comma star and H comma delta be the two groups, and which is mapping from G such a way that G tends to H, is called as a group homomorphism from A comma star to H comma delta for any A comma B belongs to G, where G of A star B which is equals to G of A delta G of B. So that is nothing but the group homomorphism, and it is represented as G of EA, that is a group's identity element should be identity element in second algebraic system, that is E of H. E of A is the identity element from the G and E of H is the identity element from that capital H. And talking about inverse element, G of A raised to minus 1 which is nothing but G of A raised to minus 1, that is the identity element. So keep in mind, you have to go with all these definitions. Now the next definition is homomorphism of semigroup and monoid. So let us see here what is meant by semigroup homomorphism. So S comma star and T comma delta be the two semigroups, and which is mapping from G such a way that S tends to T, such that for any two elements A comma B belongs to S, G of A star B which should gives you G of A delta G of B, that is called as a semigroup homomorphism. So whenever you are defining the semigroup homomorphism, you should be keep in mind that semigroup means it should having the identity property, it should having the associative property, and in the case of homomorphism, it should be mapping from one function to the another function, okay, or one semigroup to the another semigroup. So that is the terminology given to you, okay. It follows the associative property. You can see here, it follows the associative property. Yes, you can go for, okay, semigroup homomorphism is called as a semigroup monomorphism, endomorphism, isomorphism, depending on whether which is mapping from one-to-one mapping, onto mapping, one-to-one, onto mapping respectively. So on the basis of one-to-one mapping, it is called as a monomorphism. On the basis of onto, it is called as a epimorphism, and on the basis of one-to-one onto, it is called as a isomorphism. And basically, as we are discussing, it follows the associative law. You can see here two algebraic system, a comma star, s comma star, t comma delta as an algebraic system. Then a comma b comma c belongs to s, which gives you LHS is equals to RHS. Simple. This one is very simple. You have to calculate for this. Okay. It follows the associative law. Then what is meant by identity law? Let us s comma star having identity e and age belongs to s. Then s comma star to t comma delta. Then g of a star e, which is equals to g of e star a, which gives you g of a delta g of e. By using the commutative property, we have interchanged this one, and it gives you g of a. So that is nothing but the identity element. Means what? In this case, this g of e will be work as this g of e will be work as a identity element. Now, monoid homomorphism. Let m comma star comma em is the first monoid, t comma delta comma et is the another monoid, and we are mapping m to t with respect to function g. Then for two elements a comma b, which gives you g of a star b, which gives you g of a delta g of b. That is the first thing. And second one is what? G of em, that is identity element, which will maps to e of t. Okay, so that is the identity property, because as we are discussing monoid must having the identity property. So that's why we have mentioning here identity property. Now see some examples, very interesting and important examples as per the perspective of university. Prove that z comma, let's take one example. Prove that z4 comma plus 4 is a group where plus 4 is a congruence modulo of 4. So basically what is meant by congruence modulo and basically what we have to prove here, it is nothing but the group. So basically while proving the group, what we are going to discuss here, we are looking for the closure properties, or we are looking for the properties, that is associative property, then identity element, and it having the inverse property. So as we have given Z4, so Z4 is nothing but collection of 4 integers. So we are taking here I is equals to 0, 1, 2, 3. So these are the 4 integers given to you. As we know, Z4 plus 4 is a monoid which performs the operations. So basically the congruence modulo, which is performs two types of operations. First one is the congruence addition modulo, and second one is the congruence multiplication modulo. So in the case of congruence addition modulo, what we are going to do? So these are the two formulas you can see here. I plus m j, which is equals to, how it is going to perform? I plus j modulus m. So mod m means what? Up to 4 number we are going to take. So that's why this m will be equals to 4. And ij means what? Any one value from 0 to 3. 0, 1, 2, 3. So we are going to find out this addition table by congruence relation and multiplication table by congruence relation. This 0, 1, 2, 3 are called as a residual classes. So basically we having 4 classes starting from 0, 1, starting from 0 and up to the 3. So plus 4. So represent this in tabular format. So if you see here, I am highlighting this addition modulo. So in this case, this plus 4, 0, 1, 2, 3, okay, in the column 0, 1, 2, 3. So if you perform the first row and first column, that is 0, 0. 0 plus 0 is what? 0. 0 plus 0 divided by 4, which gives you 4. Then this 0, just wait. Okay, so this 0 plus 0 divided by 4, that is 0 plus 0, how many? 0. 0 divided by 4, it will gives you 0. Then take this 0 plus 1, that is 1. 1 divided by 4, which is nothing but 1. Then this 0 plus 2, how many? 0 plus 2? 0 plus 2 is equals to 2. 2 divided by 2, which is equals to 2. Then next one, 0 plus 3 divided by 4, which is equals to 3. Then go to the second row. So 1 plus 0 divided by 4, that is 1, 2, 3. And the last one, 1 plus 3. 1 plus 3, 4. 4 divided by 4. So here should be 0. We have missed to write here. Just what I am typing. So here should be 0. Okay, 0 should be there. Fine. So likewise, we are going to find out the congruence modulo with respect to the addition. And in the case of multiplication, if you go in here, this 0 into 0, how many? Previously we have taken addition, now we have to take the multiplication. 0 into 0, 0 divided by 4, which is 0. Now something into 0, all will be 0. 0 into 1 divided by 4, 0 into 2 divided by 4, 0 into 3 divided by 4. Then 1 into 0. 1 into 0 means definitely 0 divided by 4, again it will be 0. This 1 into 1. 1 into 1, 1. 1 divided by, so remainder will be 1. Likewise 1 into 2. 2 divided by 4, remainder will be 2. 1 into 3. 3 will be there. 3 divided by 4, which is 3. So likewise we have find out these values. Okay, so these are the this one is the addition modulo and next one is the multiplication modulo. This one is the addition modulo. So whatever I am highlighting, and on the right side that is the multiplication modulo. Fine. Now what we have to check, this is a group. We have drawn these tables, but what we have to suggest here, these are nothing but the groups. So for the group, you can see here, it should having, okay, so it having the identity element. 0 will be identity element for addition and 1 will be the identity element for multiplication. And as it have the following property, it is a group. So what property it bears? The first one, closure property. So whatever the values of x and y are given to you, means values which is from 0 to 3. So for all the values, it can perform the operation and it having the values in between that 0 to 3. You can see here, values are not exceeded more than the residual class. They all are belonging to 0 to 3. So that closure property, very first property, that is a closure property, is satisfied by that. Then associative property, yes, definitely it will be satisfied. Identity element, considering 0 as an identity element, it is going to satisfy that. Means 0 plus 1, you can see this one, 0 plus 1, 0 plus 0, 0 plus 1, 1, 0 plus 2, 2, 0 plus 3, 3. Means in this case, this 0 is working as an identity element. And inversibility. So if I take here this 3 plus 0, no issue, it will be 3. This 0 plus 3, again it is a 3. Means inversibility, or it is also called as a commutative property. It follows both inversibility and commutative property. So as it follows all these things, so it is called as a group. So I have checked for this addition, you have to check for multiplication also. So that is very important question as per the point of view to the examination. Keep in mind, we practice this question. Now, the next one, prove that, next question is what? Prove that Z6 plus 6, Z6 plus 6 is a group. You have to prove this. So basically we have given, how many numbers we have given, or what is the, what is the residual class? Residual class of 0 to 5, that is 6. So we have to find out here I plus 6j, which is equals to I plus j modulus of m. So m is nothing but 6. So if you see, by calculating residual classes, we got this table. And this table does not exceed the limit than the residual class. So it follows closure property as it does not exceed the limit. Then it follows associative property, it having identity element as a 0. You can see here, this 0 is working as an identity element. Okay, and it may be perform the inversibility. So this is again a group. So thank you so much for patience listening. These are the some very important question as per the point of view to the examination. So you have to do all these things for the examination, whatever we have discussed here. So what we have discussed, what is meant by algebraic system? So algebraic system, that is a S comma F1 comma F2, where S is the non-empty set and F1 F2 these are the some binary operations. In the case of algebraic system, we have seen two closure properties. For example, I comma plus comma multiplication is the algebraic system, and you have to check which operations they are performed. Basically, 4 operations are performed by addition and 5 operations are performed by the multiplication. So keep in mind that is the closure property. Then we have seen what is meant by semi-group, monoid, and what is meant by group. So keep in mind the formal definition of semi-group, monoid, and group. Then we have seen closure property with respect to one algebraic system, I comma plus comma multiplication, where we have taken I as a set of all even numbers, I as a set of all positive numbers, and I as a set of negative numbers. So for all these three, it follows the closure property. Then we have seen what is meant by homomorphism, and with respect to homomorphism, we have seen some definition, that is epimorphism, isomorphism, endomorphism, and so on. So you have to keep that in your mind. Then we have seen what is meant by monoid homomorphism. We have seen what is meant by subgroup, what is meant by homomorphism. Then with respect to the congruence relation, we have seen 2 examples. All these things are very important as per the point of view to the examination. So that's all from the chapter number 4, that is the algebraic system. Thank you so much for your patient listening.